All right, the second lecture in this unit is calculating the equilibrium constant. It's a numerical value that gives us the ratio of products raised to their coefficients divided by the reactants raised to their coefficients. This is a numerical value which we can then use to predict about a couple different things. For example, in this first problem, we see that k is equal to 16. K is greater than 1. And this tells me immediately that product formation is favored. There will be a higher concentration of products and reactants because the value of K is compared to 1 is greater than it. If it's less than 1, between 0 and 1, the smaller it gets, the less and less product formation will occur. Okay? To calculate the K, once we have the equilibrium constant expression, we simply plug it in to calculate it. So in this pictorial example, calculating Kc, we would put the products on top. Well, the products are right here. So it'd be the concentration of this substance raised to the first power because there's only one molecule represented in the picture over this substance raised to the first, all divided by the reactants now go on the bottom. Again, it's a proportion of product concentration to reactant. So as a picture, as a particular example, that would be the Kc expression. Okay, the molar concentration of each of the substance products over reactants. Okay, now if I look at the conditions and look at them right down here, I've already been told that there are 9 molecules, I believe, of this guy. And let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, there are 9 of the 3 sphere molecules with no filled in, and that there is 12 of these molecules. And there is 0 of the other 2. Okay? We'll look at equilibrium. Let's see what we have left. So we have, looks like one of these guys is left. Okay? Looking at, there's one right there. 1, 2, 3, 4. There are 4 of the other reactant molecules that are left once equilibrium is achieved. Okay, now looking at the two open circles, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. And then lastly, which should be all the other molecules, 1, 2, 3, 4, 5, 6, 7, 8. Looks like everybody's accounted for. 8. So the change was to go from 9 to 1. This guy decreased by 8 molecules. This guy went from, the second one went from 12 to 4. It too decreased by 8. The products both went from 0 to 8, so they increased by 8. You might be asking yourself, why was the change all 8? Well, the change is tied to the stoichiometry. So as this reaction proceeds either forward or backwards, initially the reaction can only go forward because there was no products present initially. So as the reaction proceeds, as we have successful collisions, both of these are going to go down by 1 for every successful collision. These are going to go up by 1. So since all of the coefficients are 1s, we have the same magnitude change, both being 8. If the coefficients are different, then these numbers would be different and they'd all correlate to the coefficients out in front. So remember, as the reaction proceeds in one direction versus the other, the change is going to have to stay tied to that stoichiometry. As successful collisions occur, certain number of molecules will be consumed and certain other molecules will be produced. Okay? Now, to calculate the value of Kc, we now plug in those numbers. So if we consider the number of molecules to be equal to the concentrations, we have, I'm going to plug in 8, 8, 1, and 4. So I have 8 times 8 over 1 times 4. 8 times 8 is 64, divided by 1 times 4 is 4. The Kc for this ends up being 16. Look her there. It matches up perfectly. Once the equilibrium constant is achieved, once the concentrations of reactants and products equals the equilibrium constant expression value, we are now at a state of equilibrium. No matter what the initial concentration of substances are, I could start with all products, I could start with all reactants, I could start with a mixture of each of them. The reaction will proceed forwards or backwards until the product quotient, until this numerical value of the products or reactants, it'll keep shifting until that product equals 16. This is now equilibrium, and the reaction will stop changing their concentrations. Okay, and that's what the equilibrium constant value tells us. Not only tells us who's favored more, in this case more product formation, but also once that numerical value is achieved by their concentrations, it no longer stops changing. All right, so real quickly, we're going to go through an example here of calculating the Kc of a specific numerical value. Okay, so it says a mixture of hydrogen and nitrogen is reacted in a vessel at 472. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of that, 2.46 of that, and 1.66 of that. From this data, calculate Kp for this expression. To calculate a Kp, products go on first, on top, and again, it's going to be partial pressure of the product raised to its coefficient, partial pressure of nitrogen to the first, partial pressure of hydrogen to the third. That is the expression. Now, if they ask me to calculate the value, I am now going to plug in chug. So the partial pressure of ammonia is 0.166. That number is going to be squared. Divided by the partial pressure of nitrogen is 2.46. And the partial pressure of hydrogen is 7.38. And that guy is cubed. So now pulling out our calculator, 0.166 squared divided by 2.46 divided by 7.38 to the third, and we get a Kp of 2.79 times 10 to the negative fifth. Kp is much, much smaller than 1, which tells me that product formation, the formation of ammonia under these current conditions, is not favorable. A K value under 1 tells me product formation is not something that's going to occur at a significant amount under the current conditions. Okay? All right, real quickly, I would like you to go ahead and try to do the next problem, A, B, and C. Okay? In the first one, calculate the value of K. In this case, these are going to be Kc's because we're looking at molar concentrations. So now I'll calculate the Kc at 127 degrees. So the conditions have changed. It's not going to be the same number. And then B and C are manipulations of that value based on how they change the reaction. So go ahead and see if you can do that problem. I'll pause the lecture now. All right, in completing the problem, again, we're going to put the concentration of ammonia on top, and it's going to be squared. Concentration of nitrogen on the bottom and concentration of hydrogen, which was given to us up above, just plugging in. The Kc ends up being 3.8 to the fourth. Okay. In part B, if you notice, the reaction is simply flipped compared to the original. Since I know the Kc at 127 degrees, if I flip it, I can use the same number, but now because I flip it, it doesn't become negative. I have to take that number to the negative 1. And taking the negative 1 just doesn't simply mean that that power of 4 is now to the negative 4. We literally have to take the inverse of 3.8 to the fourth, and we get 2.63 to the negative fifth. And then C, we took the original equation up there in A, and we now magnified by a constant of 1/2. And therefore, we take the magnitude of Kc, and we now raise it to the 1/2 power, and we get a Kc now of 190. Again, those are just manipulations of K and calculating the K constant, which is the first part of today's lecture. The second part of today's lecture is doing something which is called the ICE method, which is an acronym, stands for Initial Conditions, Change, and Equilibrium. In essence, it is a mental map that allows us to sort through the story problem, to place down all the unnecessary information, and then to figure out okay, the process in order to solve the problem. Okay? In order to do an ice problem, the first thing we do is we write the balanced equation, and then below it we write the words ICE, or ice. I would stand for what are the given initial conditions of each of the reactants and products. What is the change, as we saw from the previous problem, which is tied to the stoichiometry. And lastly, from that change, what is the concentration at equilibrium? Once I know the values in this bottom part of this table, I can use that to calculate the Kc of this chemical reaction, because these are the values of each of the substances once equilibrium is achieved. If I were to plug in the values of the initial conditions, that is not the equilibrium constant. Instead, that is called the reaction quotient, which is Q. Q is the concentration of products over reactants initially in the reaction vessel. So the Q value is the initial concentrations. The K value is what the concentrations are at equilibrium. So they can be two totally different numbers. Okay? All right, so in this problem, it says in a closed system, there is 1 to the negative third molar of hydrogen and 2 to the negative third molar iodine is placed in the vessel and is allowed to reach equilibrium. So initially, I have 1 times 10 to the negative third and 2 times 10 to the negative third molar concentrations. They make no mention of HI, and so the assumption is made that there is 0 HI in the vessel. We only put reactants in the vessel. Okay? Analysis shows that the equilibrium mixture, that the concentration of HI at equilibrium ends up being 1.87 times 10 to the negative third. I'm going to blow this up a little bit here. Okay? So the change is initially, because there are no products in the vessel, the reaction initially can only proceed in the forward direction. And therefore, the change is going to be tied to stoichiometry. This guy is going to go down or become negative. Both of these are going to be consumed because there is no product to go in the reverse order to form them. So this guy is going to go down by negative 1x, and so is this guy, because the coefficients out in front of them are 1s. The product concentration is going to go up by the stoichiometry, but there's a 2 in front of them. So for every 1 molecule of hydrogen and iodine that reacts, there's going to be 2 molecules of HX that are formed. So whatever that change is, okay, whatever that change is, for H2 and I2, the increase in change of HI is going to be plus 2x. Okay? So then the concentration of H2 at equilibrium is going to be 1 times 10 to the negative third minus x, and this is going to be 2 times 10 to the negative third minus x. I'm literally using this ice table as a way to sort through all of the information given to me in the problem. Now, from here, in order to calculate the value of Kc, I have to actually know what these concentrations are. Well, I do know the concentration of the product, so that's a good thing. But what I don't know is the concentration of the reactants, because I don't know the change. Can you look at this table right now and figure out a critical thinking or problem-solving strategy we can use to figure out what the change is? The key is the product. 0 plus 2x equals 1.87 times 10 to the negative third. Since I know the concentration of HI at equilibrium, the initial value plus the change will give me the new equilibrium value. So 2x equals 1.87 times 10 to the negative third. So if I divide by 2, the change, punching in my calculator here, ends up being 9.35 times 10 to the negative fourth. So now I can come back and figure out the concentration of H2 at equilibrium, which I'll label H2EQ, equilibrium. It's going to be 1 times 10 to the negative third minus 9.35 to the negative fourth. And we get 6.5 times 10 to the negative fifth. And the concentration of I2 at equilibrium will be 2 times 10 to the negative third minus 9.35 to the negative fourth. And we get 1.065 times 10 to the negative third. And the concentration of HI at equilibrium was already given to us, 1.87 times 10 to the negative third. So now I know the concentrations of all three of the substances, and now I can easily calculate the value of Kc for this expression. Okay? Again, the Kc expression would be the concentration of HI squared over the concentration of H2, times the concentration of I2. So now I'm going to plug in those values that I just calculated. So HI is 1.87 times 10 to the negative third squared divided by 6.5 to the negative fifth and 1.065 to the negative third. So going ahead and punching that out, I get a Kc value that is 50.5. 50.5. So that's the first example of an ice problem, how to solve it. So write the balanced equation, write the word ice, plug down all of the information given to you into the ice table. The change is tied to the stoichiometry. You have to figure out which way the change will occur. Usually one of the substances is 0, so you can immediately figure out that it has to go in the direction to make some of that because the reaction can't go in the reverse process since there's none of it present. Fill in all the information and then solve. Okay? And if they give you one of the values at equilibrium, like in this problem, this is what you'll always do. You'll use that value to figure out the value of the change and go back through, do all the mathematics, and then you'll be able to figure out the concentrations at all the equilibrium values and then plug in. And that's how we can do an ice table in which the Kc is asked to be solved for, in which one of the equilibrium concentrations are known. In these ice tables, there typically ends up being one or two problems. They give you the concentration at equilibrium of one of the substances where we can then figure out the change and work through the ice table. The second problem, which we're going to see in a little bit here, is where they give you the equilibrium constant value, and you can use that to work backwards to figure out the change. Okay? One last thing about the reaction quotient. The reaction quotient tells us what the ratio of products to reactants are initially. Up in this first problem, the initial concentration of HI was 0, so it's going to be 0 over the values that were given to us. So the Q value, the Q value of this reaction was 0. I can see that the K value now has been found out to be 50 at this reaction value. So if the Q value does not match the K value, we know that the reaction is not at equilibrium, and therefore the reaction will have to shift in a way that will need to cause the K value to be achieved. Well, I have a smaller value, 0, trying to become 50. How can I increase the value of the product, the quotient of products over reactants? This immediately tells me that I need to make more products. The reaction has to shift to make more products in order for the current ratio of products to reactants to increase. So if your Q value is less than the K value, this tells you that the current conditions is that we need to produce that the product concentration is too low. The concentration of products is too low when Q is less than K. And therefore, more products have to be made and so the reaction has to shift forward to make more products so that 0 can become 50.5. We have to have an increase in the magnitude of the value so that the equilibrium can be achieved. Opposite is true. If the Q value is greater, now the product concentration is too high. There's too much products, and that causes the Q value to be much bigger than K. And now the reaction has to shift left so that the value can decrease until equilibrium can be reestablished. If you calculate the value of Q and it equals K, we are at equilibrium. And if we are at equilibrium, we are already at equilibrium, and so there is no shift. There will be no more products or reactants formed. Whatever the concentrations of them currently are, they will remain that. Okay? So down here, what I'd like you to do in A is I'd like you to calculate. You'll notice that all of these have these little 0 symbols, which tells us that this is the initial concentration of the substances. I would like you to plug these numbers in. In essence, then you're calculating a Q value because these are concentrations that are not at equilibrium, but are at the initial concentrations of the problem. Calculate the Q value, and they tell me that the K value at the current conditions is 6.0 to the negative 2. Calculate the Q value, and based on how it compares to Kc, that should tell us if the reaction is going to shift left, shift right, or have no shift at all. So go ahead and try the problem. Pause the lecture and see what you get. All right, so this is a classic type of problem you'll see in an FRQ where they'll give you a concentration of the substances. In a previous part, you've already probably calculated the value of K, and so you plug in the numbers. You're calculating what is a Q value because you're not sure if you're at equilibrium or not. When we do so, using the numbers they've given us, the value of Q is much, much bigger, the value compared to the value of Kc. If Q is much bigger than Kc, that tells us that the product to reactant ratio is way too big. So therefore, the reaction has to shift left. The reaction has to produce more reactants. The concentration of products has to go down in order for that value, that ratio of products to reactants to decrease to the point that the K value is achieved. Okay, so product concentrations would have to be consumed, and therefore, once they're consumed to the point that the ratio ends up becoming the value of K, then equilibrium is finally established. So this is a typical type problem that you'll see in FRQ. You need to calculate a value of Q compared to K, and that is the support that you'll utilize in order to do the problems. Okay? All right, let's turn the page. So the homework for you guys is to do the next various sets of problems. There's 5 of them that I'd like you to do, but I'm going to do a couple with you guys to check your work on some different processes, okay? I'd like to do number 3 with you. But what I'd like you to do first is I'd like you to write the balanced equation and fill in the ice table. So pause the lecture and do that. Write the balanced equation, fill in the ice table with what is known. And if you want to keep working, go ahead, but then restart the lecture, and then I'll go work from there to see what we can do. All right. The balanced equation, I'm sure you wouldn't have too much problem with. You should have written the word ice next to the problem. First thing that students forget to do is you'll notice that they tell me each substance has got a mole concentration of 1 mole, and the flask is 1 liter. They'll often creep this type of stuff into you. Now, they were nice to you in the fact that they gave you a 1 liter flask, but we don't plug in moles into this table. It's a Kc, which means it's a molar concentration. So 1 mole divided by 1 liter means that each of them is a 1.0 molar concentration. They're all 1 molar. Be careful in problems in the future like this because they might change the size of the flask, and therefore, if the change of the flask is not 1, your concentrations will be vastly different than the mole quantity. So be careful there. Make sure what you plug in the ice table is a molar concentration. When we plug in 1 each, the question becomes, since there's some of each substance, which way will the reaction shift? The reaction could just as easily go left as it could go right. So what I did is they told us the K value is 5.1. If I were to plug in the concentrations of 1 and calculate a Q value, we end up getting 1 times 1 over 1 times 1, which ends up being 1. 1, the value of Q, is less than the value of K. So by comparing a Q versus K, I can predict that since KC is bigger than Q, we need more products in order to get that ratio of products to reactants up to 5.1. So I now know, because of this comparison of Q to K, that the reaction is going to go right initially until equilibrium is established. Therefore, the stoichiometry is 1, 1, 1, 1. So I'm going to minus X from both of the reactants and increase by X for both of the products. That is your completed ice table. Now, if I know the value of Kc, the next step is the expression for this reaction would be the products over the reactants. Well, I'm going to plug in everything I know. I know the value of Kc. Since the Kc is an equilibrium, I need to plug in the concentrations at equilibrium. So the concentration of CO2 is 1 plus X, 1 plus X, over 1 minus X, and 1 minus X. So now the question becomes, how can we solve this? Now some of you might ready to think about, let's go ahead and do foiling, let's do quadratic formula. All that stuff is going to take you way too much time. No, there's different tricks of the trade. Here, I need to rewrite 1 plus X as 1 plus X squared over 1 minus X squared. Because they're both two variable expressions, I can write it as a polynomial function as such. Now, because I have two square terms over each other, what I can do to isolate, instead of doing the quadratic formula, which would take me a long time, I can take the square root of both sides. So one technique that you might utilize in these ice problems is utilize the square root property. Again, this is one of the harder things you've done all year long. So this is why you have to do lots of practice on this. You just can't watch me do one example of this and think you know how to do it. Okay? So you've got to take, one technique is to utilize the square root property to solve for the variable. By taking the square root, what literally happens is the square terms eliminate, and now I don't have to worry about the quadratic formula. So now I have 1 plus X over 1 minus X equals the square root of 5.1, which is 2.26. So now I need to solve that equation for X. So please pause the lecture and go ahead and do that and see if you can solve for X appropriately. All right, so you can see my math now, and you should have gotten an X value of 0.387, and that is the change. So now I go back up into my table, and 1 plus the change gives me a concentration of CO2 and H2. The product should have a concentration of 1.387, and the concentration of CO and H2O, the reactants, should be 1 minus 0.387, which gives me 0.613. Now, if I were to take those values and now substitute them back into the Kc expression, we should end up getting a numerical value that is really close to 5.11. When I plug in these numbers and calculate, I get a value of 5.12. We're right at 5.1. A little difference is due to the rounding, but we're right where we need to be. So it's a way we can quickly check to see that our math works out. Okay? 1, 2, and that are in your pack page. One other technique, an example problem I want to show you, is number 5 in these problems. Okay? So in number 5, okay, it says NOCl decomposed to form NO and Cl2. All right, go ahead and fill in the information that is presented, and then we'll work from there. Please pause the lecture and restart to see if you've got it filled in correctly. All right, if you've done the ice table correctly, first of all, the concentration of NOCl should not be 1, but it should be 0.5 because the flask was 2 liters, and therefore 1 mole over 2 liters gives me 0.5 molar. I've got my balanced equation as shown correctly, and because there was no products present at the start of the the reaction has to proceed to the right, which means the concentration of NaCl will go down, and it's going to go down by a factor of 2x. NO is going to go up by 2x, and Cl2 will go up by 1x. Again, I simply add the initial to the change to get the equilibrium values, and then I appropriately plugged in these values into the Kc expression, and the Kc was also given to me. So right here is the point that I'm hoping some of you are able to get to. And if not, you're going to have to do a much more practice and able to go ahead through those types of steps to get even to this point. Now, we can't use the square root property because of the fact that there's a single x term here. So that's not going to work. So there's a second technique that is often used in the national exam. So there's two techniques to think about here. So if I'm given the value of Kc, and I need to find out the value of x, there's one or two techniques. One is the square root property. Can't use it here. The second concept is if your K value is very, very small, what that means then is your value of x, your change, is going to be so small that we consider it to essentially be zero. We consider the value to be so small that whatever we add or subtract to, it's going to subtract or add effectively zero. Okay? For example, 0.5 minus 2x. If that value is so small, we might get a number that's like 0.4999998. Effectively, to 3 sig figs or 2 sig figs, that number is still 0.5. It really hasn't changed that much, and that's a technique we're going to utilize. So whenever K is small, anything that we add or subtract from, we're going to say that the initial concentration is so much bigger than the change that effectively this number, the change, essentially is so small that it's zero. So by doing that, the top numbers, I can't just simply say x is 0 because then there's nothing left. Because there was 0 products to begin with, whatever the value of x is, no matter how small it is, it's still more than nothing. So those stay the same. But the bottom number becomes just simply 0.5 squared. Now this is an easy polynomial function that you can be able to solve fairly quickly. The first thing I'm going to do is I'm going to square the two things inside. And students often forget to square the 2. So 2 squared is 4. X squared is x squared times x all over 0.5 squared. Simplifying further, I get 4x cubed on top, and 0.5 squared is 0.25 equals 1.6 times 10 to the negative fifth. So now go ahead and take this algebraic polynomial function and solve for x and see if you can get the appropriate value. All right, solving for the appropriate values, you can see my work. I multiplied by 0.25 divided by 4, which ends up giving me 1.6 to the negative fifth. Then that's x cubed, so we have to take the cube root. Make sure you know how to do a cube root in your calculator, and that gives me a value of x of 0.01. Substituting that back up into the table for the equilibrium values right up here, 0.5 minus 2x, or 2 times 0.01, I get a value of 0.48 for NaCl. NO is 2 times x, which is 0.02, and Cl2 is x, which is 0.01. These are the equilibrium concentration values. And then if we want to plug those numbers back up into the expression, we should get a value of Kc that's really close to 1.6 to the negative fifth. So if you are given the K value and you are asked to solve for the x value to figure out the equilibrium concentrations, you will need to either typically use the square root property or this approximation technique where anything that we add or subtract an x from will be so small we consider it negligible. And this rule is called the 5% rule, and we'll see it more applied to acid-base equilibrium chapter 16 in a couple weeks. So based on applying this rule that since less than 5% of it will dissociate, we can assume that it's a negligible change and then can approximate the value of x utilizing this technique versus having to use the quadratic. Quadratic would give you a more precise number, but in the scope of the national exam, it would take way too much time for 1 point or 2 points to be garnered. Okay? Now I've got other problems, number 3, excuse me, 1, 2, and 4, that I'd like you to go ahead and do. I'll put those answers into Canvas after the video, and then I will have an additional worksheet on more ICE problems that I would really, really appreciate you to do. You have to do a bunch of practice, and if you do several problems of each, it's a technique that will become more comfortable to you, and you'll be able to do or have more mastery of it on both the test and the national exam. Apologize for the length of this, but as you can tell, this is a pretty detailed type of concept that you just can't spend 10 minutes on and know how to do. There's a lot of depth to each of these problems. Again, thanks.